Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is the ohm meter. Our objective is to introduce the ohm meter, a tool used to measure the resistance of an electrical circuit. Additionally, we'll introduce the Audible continuity test mode available on most DMMs. For the purposes of today's lecture, we'll be making use of the Fluke 87 Series 5 digital multimeter. This in no way is meant to be neither an exhaustive review of this tool nor an endorsement of this particular manufacturer or model. I only wish to present the function of interest on a representative example so the viewer can gain some practical exposure to this function and interpret the manner in which the results are displayed. A digital multimeter, or DMM, is a single meter that has multiple, hence the term multi, mode settings. DMMs can be used to measure both DC and AC voltage and current, resistance, capacitance, forward bias voltage of a diode, frequency, and much more. Today, we're only going to look at the ohm meter function of Fluke 87 Series 5 DMM, where an ohm meter is a device used to measure the resistance between the two terminals of interest in units of ohms. We'll examine other functions of this DMM in later lectures. The Fluke 87 Series 5 DMM is a portable or handheld multimeter meant to travel with a technician from place to place. This is in contrast to something like a BK Precision 2831E, which is a benchtop model, meaning it is meant to be plugged in at a workstation and only infrequently moved from place to place. A DMM uses a set of test probes to measure the resistance of an element placed between the two tips. The business end of the test probes can be standard pointed probes, alligator clips, or retractable hook clips. For applications with small clearances, I don't recommend using alligator clips because they're clunky and prone to accidentally touching other components in small spaces and have limited use in motor control circuits. For a small clearance circuit, an example being a circuit on a prototyping board, I'd recommend using the retractable hook clips. In super tiny clearance circuits, you can actually hook a wire to the end of the clip and now use that as your test point. For circuits with larger clearances, one can use the alligator clips or the pointed probes. The pointed probes are super handy for motor control elements like contactors and overloads. Often the terminals of contactors and overloads are located inside protected wells. The pointed probe can reach the bottom of the well and a technician can take measurements safely without ever being exposed to energized conductors. Before we make use of the ohm meter function, we need to insert the leads. Black lead into the black hole. Red lead into the red hole, indicated with an ohm, shorthand for units of resistance over it. Yes, you can put a black lead in a red hole or a red lead in a black hole, just like you can put a hat on your foot, but that is not its intended purpose. To place the Fluke 87 Series 5 DMM in ohm meter mode, turn the selector switch to the position identified with an ohm symbol. One can enable the backlit display in low light conditions by pressing the leftmost display light button in the second row of functions along the top. The DMM displays OL, which is shorthand for overload, indicating the resistance between the two probes is too great to be measured, which implies an open circuit. This is this DMM's way of telling us that there is no conductive path between the two probes. Different types of DMMs might indicate an open by saying overload, blinking digits, or straight up spelling out open on the display. When I touch the probes together, resistance plummets, indicating the test leads present an extremely low resistance path. This is an excellent way of function testing the leads. Leads with a break would indicate an open circuit and would not be suitable for testing the resistance of other elements. Now that we're certain we've got a functional set of probes, let's test the resistance of a couple objects. Before doing so, let me explain a couple of important rules about using an ohm meter. First, the item under test must not be energized, i.e. it needs to be powered off if you don't want to destroy your ohm meter. Second, the item needs to be removed from a circuit if you wish to obtain a valid resistance reading. More on this in a moment. Finally, use the checklist. I am not urging you use this checklist every time. I am demanding you use this checklist every time. This checklist will save your measurement equipment and circuit a lot of costly downtime and may potentially save your life. I am not overstating the benefits of using this checklist. Use the checklist. Think about it. Really think about it. Take your time and think before you act. The checklist has 4 steps. Follow them 1 through 4 and you will get it right every single time. Skip a step, do a step wrong, or do a step out of order, and you will get it wrong every single time. Function, leads, range, placement. Function. The DMM is in the ohm meter mode. This is our desired function. Leads. We put the leads in the right place. Black lead in the common hole, red lead in the hole indicated with an ohm symbol. What about range? Don't worry about it. The Fluke 87 is auto-ranging, meaning it automatically picks an appropriate range to obtain the most precise results. Now, you can force it out of auto-range mode into manual mode if you want to, but we'll keep it as is. Finally, placement. All you need to do to check the resistance of an object is to place the test probes from terminal to terminal. On a very basic level, ohm meters are commonly employed to check the continuity of a circuit. Forget measuring resistance in units of ohms. Is something connected or is it not connected? Opens, i.e. items with no conductive path, would be identified with an overload on the display. Items with a conductive path would be identified with a small resistance value on the display. Consider this length of wire. The ohm meter indicates this wire has an extremely low resistance value, implying that this wire is conductive and it is contiguous with no breaks. Consider, however, this length of wire that's been subjected to some mechanical abuse. Is it still in one piece? Outwardly, it appears no different than our previous wire, and you might initially suspect it's fine. However, the ohm meter reveals a dark secret about that wire. This wire is in fact broken inside the insulation, and no conductive path exists from end to end. In addition to numerical measurement of resistance, most DMMs offer an audible continuity test. In summary, if it beeps, there's a connection. If it doesn't beep, there's no connection. To place the Fluke 87 into audible continuity test mode, press the audible ring button in the second row of top function buttons while in ohm meter mode. When the probes are separated, the DMM is silent. When I touch them together, the DMM produces a tone. Annoying, right? The audible continuity test is actually pretty handy because you can check the continuity of a mess of wires without having to glance up and look at the screen to interpret the numbers. This being said, imagine the joy of running a lab with 16 students all in audible continuity test mode. It is a small wonder that I don't break more furniture against the wall than I do already. Let's use the audible continuity tester to check the continuity of a circuit breaker, a type of heavy-duty switch. With the circuit breaker open, the audible continuity tester remains silent. When I close the circuit breaker, the audible continuity tester indicates continuity exists. Again, a continuity test simply checks whether or not a connection exists, but does not provide a numerical measurement of resistance. To obtain a numerical measurement of resistance, we need to return to ohm meter mode. Consider the following set of 3 resistors exhibiting these 4-band color codes: red, red, brown, gold; orange, orange, brown, gold; and finally, yellow, purple, brown, gold. See if you can use your understanding of the 4-band resistor color code to determine the nominal or nameplate resistance value for these 3 resistors. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. Red, red, brown, gold means this resistor has a nominal or nameplate resistance of 220 ohms plus or minus 5%, meaning it might actually be between 209 and 231 ohms. Orange, orange, brown, gold means this resistor has a nominal or nameplate resistance of 330 ohms plus or minus 5%, meaning it might actually be between 313.5 ohms and 346.5 ohms. Finally, yellow, purple, brown, gold means this resistor has a nominal or nameplate resistance of 470 ohms plus or minus 5%, meaning it might actually be between 446.5 ohms and 493.5 ohms. Let's use the ohm meter to test if these resistors are inside their expected tolerance range. When placed between the probes of the ohm meter, resistor A with a nominal value of 220 ohms appears to have a resistance of 223.7 ohms. This is inside our expected range. Similarly, when placed between the probes of the ohm meter, resistor B with a nominal value of 330 ohms appears to have a resistance of 331.3 ohms. This is inside our expected range. Finally, when placed between the probes of the ohm meter, resistor C with a nominal value of 470 ohms appears to have a resistance of 471 ohms. This is inside our expected range. Let's now examine series arrangements of resistors. See if you can calculate the total resistance of A in series with B, B in series with C, and finally A, B, and C all in series with one another. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. A in series with B should present a total resistance of approximately 555 ohms. B in series with C should present a total resistance of 802.3 ohms. Finally, A, B, and C in series with each other should present a total resistance of 1026 ohms, or more appropriately, approximately 1 kilo ohm. When placed between the probes of the ohm meter, the series combination of resistors A and B appears to present a resistance close to our theoretical calculations. Similarly, when placed between the probes of the ohm meter, the series combination of resistors B and C appear to present a resistance close to our theoretical calculations. Finally, when placed between the probes of the ohm meter, the series combination of resistors A, B, and C appears to present a resistance close to our theoretical calculations. You will note the order of series elements does not influence total resistance. For example, the series combination of A, B, and C would have the same total resistance as would ACB, BAC, CAB, or any other possible permutation of A in series with B in series with C. In summary, series resistances add up, and the order in which you add them does not influence total resistance in any way, shape, or form. Let's now discuss the influence of opens and shorts inside series circuits. First, let's examine opens. Consider the series combination of A, B, and C, where there is a gaping hole between A and B. This is an open circuit. An ohm meter demonstrates that this series combination of three elements, including an open, now presents an infinite resistance because no conductive path exists. Consider the open being relocated between B and C. Again, the ohm meter demonstrates that this series combination of three elements, including an open, now presents an infinite resistance because no conductive path exists. In summary, an open anywhere in a series path completely severs that path. It makes sense. A series or inline path with a rupture or open anywhere in that single path does not have a conductive path. Let's now deal with shorted elements in series circuits. A short is a low resistance around or in parallel with an element. Consider resistor A, ordinarily a resistance of roughly 220 ohms, with a 0 ohm wire in parallel, or around it. Think about it. When presented with a 220 ohm path or a 0 ohm path, through which path would a majority of electrons travel? Undoubtedly, the 0 ohm short presents a far easier means of travel from end to end. The ohm meter confirms this fact. Shorted resistor A now presents a small resistance path. If we include shorted resistor A in the series combination of all three resistors, the ohm meter demonstrates the total resistance of the series path is now only the series combination of B and C, implying that shorted resistor A is essentially excluded from consideration. What happens if we return resistor A to its original configuration and short resistor B? The ohm meter demonstrates the total resistance of the series path is now only the series combination of resistor A and resistor C, implying that shorted resistor B is essentially excluded from consideration. In summary, a shorted element in a series path removes only that shorted element from consideration. Let's now examine parallel arrangements of resistors. See if you can calculate the total resistance of A in parallel with B, B in parallel with C, and finally A, B, and C all in parallel with each other. By all means, pause the lecture and try this on your own. If you're tracking, you should obtain the following values. The parallel combination of A and B should present a total resistance of approximately 133.5 ohms. The parallel combination of B and C should present a total resistance of approximately 194.5 ohms. And finally, A, B, and C, all in parallel with each other, should present a total resistance of approximately 104.0 ohms. In each of these occasions, note how the total resistance of a parallel combination is always smaller than the smallest resistor. Let's use the ohm meter to verify these theoretical calculations. When placed between the probes of the ohm meter, the parallel combination of resistors A and B appears to present a total resistance close to our theoretical calculations. Similarly, when placed between the probes of the ohm meter, the parallel combination of resistor B and resistor C appears to present a total resistance close to our theoretical calculations. Finally, when placed between the probes of the ohm meter, the parallel combination of resistors A, B, and C appear to present a total resistance close to our theoretical calculations. You'll note the order of parallel elements does not influence total resistance. For example, the parallel combination of A, B, and C would present the same total resistance as would ACB, BAC, CAB, or any other possible permutation of A in parallel with B in parallel with C. In summary, the arrangement of individual resistances does not influence total resistance of a parallel arrangement in any way, shape, or form. Let's now discuss the influence of opens and shorts inside parallel circuits. First, let's examine opens. Consider the parallel combination of A, B, and C, where A is dangling out in space. The ohm meter demonstrates that this parallel combination now presents a total resistance equivalent to only resistor B and C in parallel with one another. It makes sense, because resistor A is not really in this parallel circuit. Consider the parallel combination of A, B, and C, where now resistor C is dangling out in space. The ohm meter demonstrates that this parallel combination now presents a total resistance equivalent to only resistor A and B in parallel with one another. Again, it makes sense because resistor C really isn't in this parallel combination. In summary, an opened element in a parallel configuration removes only that opened element from consideration. Opens can occur in other places in parallel circuits. Consider the parallel combination of A, B, and C, where the entire parallel combination is dangling out in space. The ohm meter demonstrates that this parallel combination now presents an infinite resistance because the open has severed any and all paths through everything. Let's now deal with shorted elements inside parallel circuits. A short is a low resistance path around or in parallel with an element. As previously, consider resistor A, ordinarily a resistance of approximately 220 ohms with a 0 ohm wire in parallel. The ohm meter demonstrates shorted resistor now presents a small resistance path. If we include a shorted resistor A in the parallel combination of all three resistors, the ohm meter demonstrates the total resistance of the parallel combination is now extremely low, implying that shorted resistor A is effectively shorting out the entire parallel combination. What happens if we return resistor A to its original configuration, short out resistor C? The ohm meter demonstrates the total resistance of the entire parallel combination, including the shorted element, is now extremely low, again implying that a shorted resistor C has effectively shorted out the entire parallel combination. In summary, a shorted element in a parallel configuration effectively shorts out the entire parallel combination. Moving on. Recall that the element being measured by an ohm meter must be depowered and must be removed from a circuit. Let's use a different type of circuit to demonstrate this fact. Consider a series parallel combination of resistors A, B, and C, where resistor A and B are in parallel with one another, and this parallel combination is in series with resistor C. One can simplify the original series parallel circuit as an imagined resistor R single prime being the parallel combination of RA and RB in series with resistor C. The parallel combination of resistor A and B presents a resistance of 133.5 ohms. The total resistance of this series parallel circuit is our imagined resistor R single prime in series with resistor C. When our imagined resistor R single prime is taken in series with resistor C, we might expect the total resistance of this series parallel combination to be 604.5 ohms. The ohm meter confirms this fact to a reasonable degree of accuracy. Note resistor A and B are in parallel with one another, and this parallel combination is in series with resistor C. Let's use this circuit to examine the measurement of resistances internal to a larger circuit. If we wanted to use the ohm meter to check the resistance value of individual resistor A, still inside the series parallel circuit, the ohm meter reads an incorrect value of roughly 133 ohms. 133 ohms? I thought resistor A was a 220 ohm resistor. Why is the ohm meter giving us bad data? I'll tell you why. The ohm meter is being used incorrectly. To measure the resistance of an individual element, that element must be removed from the circuit. You know that the ohm meter is reading the parallel combination of resistor A and B, and not just the resistance of A, as we intend. In order to measure the resistance of just resistor A, we need to isolate resistor A by removing one or both terminals from the circuit. With resistor A effectively isolated, the ohm meter now reads just the resistance of resistor A and nothing else. In summary, an element must be isolated from the circuit for an ohm meter to obtain a valid resistance reading. Another complication exists when isolating elements from a circuit. Consider a DC power supply attached to resistor A. Even in the depowered state, this source will improperly influence resistance measurement because an unseen internal resistance through the source. If you want to think of it this way, imagine the source's internal resistance as an unseen resistor in parallel with resistor A. When the ohm meter is used to check the resistance of resistor A still hooked to the source, the ohm meter reads an incorrect value of roughly 180 ohms. Why is the ohm meter giving us this incorrect value? I'll tell you why. The ohm meter is being used incorrectly. In order to measure just the resistance of resistor A, we need to isolate resistor A from the source by removing one or both terminals from the source. With resistor A effectively isolated from the source, the ohm meter now reads just the resistance of resistor A and nothing else. Again, an element must be isolated from the circuit, including the source, for the ohm meter to obtain a valid resistance reading. Before we bring this lecture to a close, let's talk about the lower and upper extremes of resistance measurement. At the low end of the resistance spectrum, consider a length of thick, highly conductive cable. At the high end of the resistance spectrum, consider the rubber or plastic coating of insulation surrounding a wire. Regarding measurement of these two low resistance and high resistance extremes, do you think any measurement obtained using ordinary DMM would be accurate? Not even remotely. If you required exact, accurate measurements of such small or such large resistance magnitudes, one would have to use special equipment purposely designed to measure this level of detail. Such a piece of equipment would be an ohm meter, but they'd be ohm meters designed to handle either the lower or the upper range, not both. An ohm meter designed to measure extremely low resistance paths, like a transmission line or a lightning rod, is unsurprisingly called a low resistance ohm meter, whereas an ohm meter designed to measure extremely high resistance paths, like insulation surrounding a motor winding, is called a meg-ohm meter. Oftentimes, you'll hear a meg-ohm meter referred to as a megger, after the company that makes an extremely popular line of meg-ohm meters. Such special purpose tools are a little above our current level of understanding right now, but we'll come back to discuss these tools in much later lectures. Right now, you simply need to be aware that general purpose DMMs in ohm meter mode have limitations inside of which they are intended to operate accurately, and outside of which they won't. Alright, that about wraps it up for a general discussion of the DMM ohm meter function. Remember to RTFM. Read the fine manual about your specific DMM, and always, always, always use the function, leads, range, placement checklist every time you employ it. You'll be glad you did. In conclusion, this lecture took a close look at the ohm meter function of the Fluke 87 Series 5 digital multimeter. We discussed basic operations of an ohm meter, audible continuity testing, and limitations and special considerations of ohm meters. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.